What if everything we know about black holes is wrong? Tonight, we're going to explore the most massive black hole ever discovered, one so impossibly large it shouldn't exist according to our current understanding of physics. You've probably heard about black holes countless times, those mysterious cosmic vacuum cleaners that swallow everything, even light itself. But here's what most people don't realize. Astronomers recently found a black hole so massive it breaks every rule we thought governed how these cosmic monsters could form and grow. By the end of this journey, you're going to understand exactly why this discovery is forcing scientists to rewrite the fundamental laws of the universe. Before we dive in, if you enjoy these kinds of cosmic explorations, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Get comfortable. Let's begin. You've probably heard about black holes countless times, those mysterious cosmic vacuum cleaners that swallow everything, even light itself. But here's what most people don't realize. Astronomers recently found a black hole so massive it breaks every rule we thought governed how these cosmic monsters could form and grow. And to understand why this discovery is forcing scientists to rewrite the fundamental laws of the universe, we need to begin at the very edge of human comprehension, in a realm where our most basic intuitions about size, mass, and reality itself completely fall apart. The universe we can observe stretches for 57.8 billion miles in every direction. No, wait. Let me put that differently, because that number means nothing to you. The observable universe extends for approximately 93 billion light-years in all directions, a distance so vast that if light itself, traveling at 186,000 miles per second, started its journey at the moment of the Big Bang, it would still be racing toward us across this incomprehensible void. To help you visualize this immensity, imagine that each galaxy in the cosmos was reduced to a single grain of sand. To represent our observable universe, you would need billions upon billions of beaches, each one stretching beyond every horizon you've ever seen. And even then, you'd fall short of capturing the true scale of what surrounds us in every direction. Our galaxy, the Milky Way, contains approximately 400 billion stars. 400 billion. That's more stars in our galaxy alone than there are trees on Earth, more than there are grains of sand on every beach you've ever walked. Each one of those stars is a nuclear furnace, many of them larger and more powerful than our Sun. And yet our entire galaxy, with all its stellar glory, is just one among trillions in the observable universe. If you could somehow travel at the speed of light, the fastest anything can move through space, it would take you 100,000 years to cross our galaxy from one edge to the other. Think about that for a moment. Light that left one side of the Milky Way when your ancestors were painting caves would only now be reaching the opposite edge. Our Earth orbits what astronomers call a perfectly ordinary star, positioned about 26,000 light-years from the galactic center, out in what we might call the cosmic suburbs. We're not at the bustling downtown core of our galaxy, nor are we lost in some remote galactic countryside. We occupy a middle ground close enough to witness the grand celestial machinery at work, yet far enough away to avoid the more violent neighborhoods near the galactic center. Consider the scale of our own solar system for a moment, from the Sun to the outermost reaches where its influence finally fades. Our cosmic neighborhood measures roughly 100,000 astronomical units across. One astronomical unit is the distance from Earth to the Sun, about 93 million miles. So our solar system spans some 9.3 trillion miles from edge to edge. And yet this entire domain, which seems so vast from our earthbound perspective, would fit 63,000 times into the distance to just our nearest stellar neighbor, Proxima Centauri. Here's another way to picture this cosmic emptiness. If our Sun were shrunk down to the size of a basketball sitting in your driveway, Earth would be a peppercorn 75 feet away. The next basketball, Hauptbahnstadt, representing the nearest star, would be sitting in a city 2,400 miles away. This is the fundamental nature of space, not the crowded stellar neighborhoods depicted in science fiction, but an ocean of emptiness punctuated by occasional islands of matter and energy. If we compressed the entire history of the cosmos into a single year, with the Big Bang occurring at the stroke of midnight on January 1st, humanity would appear only in the final moments of December 31st, at 11:59 p.m. and 58 seconds. Our entire recorded history, from the first cave paintings to the moment you're reading these words, would flash by in less than the time it takes you to blink. And it's within this impossible scale that we encounter objects that challenge not just our sense of size, but our very understanding of reality itself. At the smallest extreme of the cosmic hierarchy exist theoretical black holes, so tiny they could fit in your pocket, yet so massive they contain the weight of entire mountains compressed into spaces smaller than atoms. These primordial black holes, if they exist, represent the first great collapse of human intuition about the relationship between size and mass. Picture holding a coin in your palm, perhaps a quarter. Now imagine that this coin-sized object contains not the few grams of metal you'd expect, but the entire mass of Mount Everest, all 162 billion pounds of rock and ice compressed into a space no bigger than the change in your pocket. A black hole the size of a ping-pong ball would contain the entire mass of our planet, all 13 sextillion pounds of rock, metal, water, and atmosphere that make up Earth, crushed into a sphere small enough to hold in your hand. The density required to achieve this compression transcends completely our everyday experience with any solid, liquid, or gas. There is simply nothing in your daily life that can prepare your mind for such extreme concentration of matter. These microscopic monsters would distort space-time so severely that the very concepts of up and down, inside and outside, would lose all meaning near them. The gravitational pull of such an object would be trillions of times more intense than anything you've ever experienced on Earth's surface. If you weigh 150 pounds standing on Earth, the same gravitational field would stretch you with a force of hundreds of trillions of pounds. Despite containing planetary masses, these miniature black holes would be completely invisible to your eyes. You could hold one in your hand and see nothing but empty space. No light escapes their gravitational grip to reach your retinas. They would be detectable only through their gravitational effects on the space around them, like invisible hands rearranging the cosmic furniture. The temperature of these smallest black holes would be astronomical, hotter than the cores of the most massive stars in the universe. According to Stephen Hawking's calculations, they would radiate energy at temperatures reaching billions of degrees Fahrenheit. If such an object existed anywhere near Earth, it would evaporate in an explosion more powerful than every nuclear weapon ever built, detonating simultaneously. Quantum mechanics suggests that the vacuum of space itself seethes with virtual particle pairs, constantly appearing and disappearing in a dance too brief and subtle for us to observe directly. Some theories propose that this quantum foam might spontaneously create miniature black holes, each existing for only the briefest instant before evaporating back into the void. These theoretical objects would represent the absolute lower limit for black hole formation, the smallest possible distortions in the fabric of space-time. But here's where our journey becomes truly extraordinary. Contrasting sharply with these microscopic enigmas, some black holes grow to scales that challenge not just our intuition, but the very limits of language itself. The gulf between the smallest and largest known black holes spans more than 60 orders of magnitude in mass and size, a range so vast that if the smallest black hole were an ant, the largest would outweigh our entire planet. Each step up this cosmic ladder reveals new principles of physics and systematically destroys our attempts to understand through familiar analogies. It's like climbing a mountain where each new altitude operates by completely different rules. What worked at sea level becomes useless at 10,000 feet, which becomes useless again at 30,000 feet. This progression of sizes functions like a cosmic staircase, where each step multiplies the mass by millions or billions. And here's something remarkable. While the tiniest black holes evaporate almost instantly, releasing their energy back to the universe in brilliant flashes, the largest ones grow eternally, accumulating matter and energy from their surroundings over billions of years. They are the immortals of the cosmos, growing larger and more powerful with each passing eon. This temporal disparity means that only the giants survive long enough to be observed by our telescopes today. The small ones disappeared long ago in bursts of Hawking radiation, leaving behind only the theoretical possibility of their existence and the mathematical equations that described their brief lives. Nature, it seems, imposes fundamental limits on how small black holes can be. Quantum effects prevent anything smaller than a certain threshold. But remarkably, there appears to be no upper restriction on how large they can grow. This asymmetry in cosmic law creates a universe where the biggest objects can become unimaginably vast, while the smallest are constrained by the granular nature of reality itself. Each category of black hole reveals different aspects of gravity's extreme behavior, from quantum effects at microscopic scales to the galactic dynamics that structure the entire cosmos. The smallest ones show us how quantum mechanics and gravity clash at the tiniest scales. The largest ones demonstrate how individual objects can influence the formation and evolution of entire galaxies containing hundreds of billions of stars. Studying these objects forces us to confront the absolute limits of known physics and question our most basic assumptions about reality. They exist at the intersection of our most successful theories, Einstein's general relativity and quantum mechanics, yet they also reveal the deep tensions between these frameworks that physicists are still struggling to resolve. We begin this journey at the very edges of human perception, preparing to discover how matter can collapse beyond any imaginable limit, creating objects so extreme they bend the laws of physics to their will. And to understand how the most massive black hole ever discovered came to violate everything we thought we knew about these cosmic monsters, we must first encounter the final guardians of matter itself. Neutron stars, the universe's last desperate attempt to prevent total gravitational collapse. Neutron stars represent the ultimate stronghold of matter before complete gravitational surrender becomes inevitable. These extraordinary objects are nature's most extreme experiment in compression, concentrating 1.4 times the mass of our entire Sun into spheres measuring just 12.4 miles across. Imagine taking every mountain, ocean, continent, and cloud on Earth, along with the Sun itself in all its nuclear fury, and crushing it all down until it fits within the boundaries of a single city. The density achieved in these stellar remnants transcends anything in your everyday experience. A neutron star packs approximately 500 million tons into every cubic inch, denser than the nucleus of any atom. To put this in perspective that your mind might somehow grasp, a single teaspoon of neutron star material would weigh roughly 6.6 billion tons on Earth. That's equivalent to taking a mountain the size of Mount Everest and compressing it until it fits on a spoon. The surface gravity of a neutron star creates forces 200 billion times stronger than what you experience standing on Earth. If you could somehow stand on such an object, though you'd be crushed to subatomic particles instantly, dropping a marble from just 0.04 of an inch above the surface would release energy equivalent to a nuclear bomb. Your body weight of, say, 150 pounds would become 30 trillion tons under such gravitational stress. At these densities, individual neutrons, the particles that normally hide safely within atomic nuclei, are compressed until they touch each other directly. All the empty space that normally exists between subatomic particles, the vast architectural void that makes up most of ordinary matter, simply ceases to exist. It's as if the universe's fundamental building blocks have been squeezed beyond their normal limits, forced into an intimacy that defies the usual rules of physics. Some of these neutron stars spin with impossible precision, sending lighthouse beams of radiation sweeping across space. These pulsars, as astronomers call them, arrive at Earth with timing more accurate than our most sophisticated atomic clocks. Picture a cosmic lighthouse the size of Manhattan, spinning hundreds of times per second. Its beam so perfectly calibrated that we can detect the arrival of each pulse down to billionths of a second. The fastest known pulsars rotate 700 times per second, 700 complete rotations every single second. A point on the surface of such an object would be traveling at roughly 15% the speed of light, creating conditions so extreme they challenge our understanding of how solid matter can possibly hold together under such centrifugal forces. These spinning neutron stars generate magnetic fields trillions of times more powerful than any magnet ever created on Earth. If a neutron star with a typical magnetic field were placed halfway between Earth and the Moon, it would erase every credit card, hard drive, and electronic device on our planet instantly. The magnetic field would literally pull the iron from your bloodstream. When two neutron stars spiral into each other in a cosmic death dance, the resulting collision releases more energy than hundreds of millions of supernovas exploding simultaneously. These catastrophic mergers forge the heavy elements that make our technological civilization possible. The gold in your jewelry, the platinum in your car's catalytic converter. All of it was born in the nuclear furnace of colliding neutron stars, then scattered across space in gravitational waves that ripple through the fabric of reality itself. But even neutron stars, for all their extreme resilience, have limits. The Tolman-Oppenheimer-Volkoff limit establishes that approximately 2.16 solar masses represents the absolute maximum weight that neutron degeneracy pressure can support. Beyond this critical threshold, no force known in nature can resist the inexorable pull of gravity. The stellar remnant crosses a point of no return. Above that limit, gravitational collapse becomes unstoppable. The neutron star's heroic resistance finally fails, and matter begins its final surrender to the ultimate force in the universe. The transition from neutron star to black hole happens instantaneously, not over minutes or hours, but in a cosmic eye blink that erases all information about the original matter forever. Stellar mass black holes emerge from this collapse with masses typically ranging from 3 to 50 times that of our Sun, depending on the size and composition of the original star that died. The smallest confirmed black hole, designated XTE J1165 Ferriopar 500, contains approximately 8 solar masses compressed into a region with a radius of just 14.3 miles. This Schwarzschild radius marks the event horizon, the point of absolute no return where the curvature of spacetime becomes so extreme that not even light can escape. Think about what this means for a moment. Light, which travels at 186,000 miles per second and can circle our entire planet 7.5 times in 1 second, becomes trapped. The gravitational field is so intense that it curves space itself into a closed loop, creating a region from which no information can ever return to the outside universe. Anything crossing this event horizon experiences something called spaghettification, a process as violent as its name suggests. The gravitational field varies so dramatically across even small distances that an object falling feet first would find its feet pulled thousands of times harder than its head. This differential stretching, technically known as tidal force, would elongate you vertically while compressing you horizontally, transforming any recognizable matter into streams of subatomic particles long before reaching the center. At the theoretical heart of every black hole lies a mathematical impossibility called a singularity, a point where density and space-time curvature become infinite, where all known laws of physics break down completely. It's not just that we don't understand what happens there, it's that our most fundamental equations literally produce meaningless results, infinite values that suggest we're missing something crucial about the nature of reality itself. The experience of falling into a black hole reveals one of the strangest features of Einstein's universe, the relativity of time. An outside observer watching you fall would see you slow down as you approach the event horizon, your image freezing forever at the boundary as your light becomes infinitely redshifted. To that observer, you never quite cross the horizon. You fade away, becoming dimmer and dimmer until you disappear. But from your perspective, falling inward, the journey to the central singularity would take only milliseconds. You would experience time normally while the universe outside appears to speed up dramatically. This isn't science fiction speculation, it's a direct consequence of Einstein's equations, verified by countless experiments and observations. Black holes themselves emit no light, making them invisible against the cosmic background. We detect them only through their gravitational effects on surrounding matter. Material falling into a black hole doesn't simply disappear quietly. It forms what astronomers call an accretion disk, a swirling maelstrom of superheated matter spiraling inexorably inward. As material in this disk accelerates to velocities approaching the speed of light, friction heats it to temperatures of millions of degrees Fahrenheit, causing it to emit intense X-ray radiation that our telescopes can detect across vast cosmic distances. These accretion disks shine brighter than entire stars, making black holes among the most luminous objects in the universe despite being fundamentally dark. Rotating black holes create effects that seem to defy common sense. The spin of a Kerr black hole literally drags space-time around with it, like honey being stirred by a spoon. This frame-dragging effect, formerly called the lens-thirring effect, means that space itself is rotating near the black hole. Nothing can remain stationary relative to the distant universe within a certain distance of a spinning black hole. Some black holes rotate so rapidly they create what physicists call an ergosphere, a region outside the event horizon where the dragging of spacetime becomes so extreme that everything must rotate along with the black hole whether it wants to or not. Within this strange realm, objects can actually extract energy from the black hole's rotation through a process discovered by Roger Penrose. This energy extraction mechanism can theoretically harvest up to 29% of a black hole's total mass energy, making it the most efficient power source known to physics. This process powers some of the most spectacular phenomena in the universe, relativistic jets that stream from black holes at nearly the speed of light, carrying energy across distances measured in light years and sculpting the intergalactic medium. These stellar mass black holes, born from the deaths of individual massive stars, establish the foundation for understanding how gravity shapes cosmic structure on progressively larger scales. They are the building blocks from which even more extreme objects will emerge, objects so massive they will challenge not just our intuition about size and scale, but our fundamental understanding of how such monsters could possibly form in the first place. But how do these stellar remnants grow beyond their humble beginnings to become the supermassive titans that rule galactic centers? The answer lies in two primary mechanisms that operate over cosmic time: the slow, steady accumulation of surrounding matter and the violent, spectacular mergers with other black holes. Black holes grow through two fundamental processes: the continuous accretion of surrounding material and catastrophic collisions with their own kind. Think of it as cosmic metabolism. Some growth happens through steady feeding, while dramatic growth spurts occur through spectacular mergers that reshape the gravitational landscape of entire regions of space. The accretion of interstellar material happens slowly, almost imperceptibly by human standards. A stellar mass black hole might accumulate just fractions of a solar mass over millions of years, gradually growing as it captures gas, dust, and the occasional star that ventures too close to its gravitational domain. This process requires immense patience. The black hole sits like a cosmic spider, waiting for material to fall into its web. But when two massive stars in a binary system evolve and both collapse into black holes, something far more dramatic begins to unfold. These paired black holes find themselves locked in an orbital dance, spiraling inexorably toward each other as they radiate away energy in the form of gravitational waves, ripples in the very fabric of space-time itself. These gravitational waves carry energy away from the system, causing the orbital decay to accelerate. What begins as a leisurely dance over millions of years becomes a frantic spiral in the final moments, with the two black holes whirling around each other hundreds of times per second before their final merger. The process is like two cosmic whirlpools being drawn together, each one distorting space-time more severely as they approach. In 2015, the LIGO detectors achieved something that seemed impossible. They measured gravitational waves with a precision of 1/10,000th the diameter of a proton. To put this in perspective, it's like measuring the distance to the nearest star to an accuracy smaller than the width of a human hair. The first detection, designated ʻOumuamua, captured the final moments of a merger between black holes containing 36 and 29 solar masses, respectively. The collision created a single black hole with 62 solar masses. But wait, 36 plus 29 equals 65, not 62. What happened to those missing 3 solar masses? They were converted entirely into energy, according to Einstein's famous equation E=mc2, and that energy was released as gravitational waves in the final fraction of a second of the merger. 3 entire stars' worth of mass became pure energy in moments. To help you grasp this magnitude, that energy release momentarily exceeded the combined luminosity of every single star in the observable universe. For a brief instant, this collision outshone trillions of galaxies, each containing hundreds of billions of stars, though the energy was released not as light, but as ripples in space-time itself. During the final merger, the frequency of gravitational waves increased from 35 Hz to 250 Hz in just 0.2 seconds. This cosmic crescendo represented the final spiral dance accelerating to its inevitable conclusion. After the merger, the newly formed black hole rang like a cosmic bell, vibrating at characteristic frequencies as it settled into its final configuration, radiating gravitational waves that carried away the last traces of its violent birth. These successive mergers can create what astronomers call intermediate mass black holes, containing hundreds or thousands of solar masses. These objects represent the evolutionary link between the stellar mass black holes we've just discussed and the supermassive giants that dominate galactic centers. They are the adolescents in the black hole family tree, no longer newborns but not yet fully mature titans. Dense globular clusters provide perfect nurseries for these intermediate black holes. These ancient stellar cities, containing hundreds of thousands of stars packed into regions just a few dozen light years across, facilitate multiple gravitational interactions that can produce intermediate mass black holes through sequential mergers. Imagine a cosmic billiard table where the balls are black holes and occasional collisions create ever larger players in the game. As black holes grow, their gravitational influence expands proportionally. A black hole containing 100 solar masses possesses an event horizon with a radius of roughly 186 miles, comparable to the size of large metropolitan areas like Los Angeles or New York. Its gravitational reach extends much further, capturing material from distances that would have been impossible for smaller black holes to influence. The accretion disks around these intermediate black holes can extend for thousands of miles, glowing intensely in X-rays as material heats up during its final plunge toward the event horizon. Material orbiting close to the horizon completes an orbit in milliseconds, creating rapid variations in the observed luminosity that serve as signatures of the extreme gravitational environment. The efficiency of converting matter to energy through accretion can reach 42% for maximally rotating black holes, far exceeding the 0.7% efficiency of nuclear fusion that powers stars. This makes black hole accretion the most efficient energy production mechanism known to physics. No other process in the universe can extract such a large fraction of a particle's rest mass and convert it to usable energy. Relativistic jets from intermediate black holes can extend for dozens of light years, influencing star formation patterns across entire regions of their host galaxies. These jets carry magnetic fields and high-energy particles at velocities approaching the speed of light, heating surrounding gas and sometimes suppressing star formation while triggering it elsewhere through shock waves and turbulence. Despite their theoretical importance, observational evidence for intermediate mass black holes remains frustratingly scarce. They are detected primarily through ultraluminous X-ray emissions in distant galaxies, sources too bright to be powered by stellar mass black holes, yet not quite massive enough to be the supermassive giants found in galactic centers. They represent a missing link that astronomers are actively hunting. Computer simulations suggest that some intermediate black hole seeds might have formed directly in the early universe through a process called direct collapse. In the cosmic dawn, when the universe was young and metal-free, massive clouds of primordial hydrogen gas containing 100,000 solar masses could have collapsed directly into black holes without ever forming stars first. These heavy seeds would explain how supermassive black holes could grow so rapidly in the first billion years after the Big Bang. If you start with a seed containing thousands rather than tens of solar masses, you have a significant head start in the race to become a supermassive giant before the universe becomes too old and spread out to support such rapid growth. Black holes in the process of rapid growth create their own feedback mechanisms that can regulate their feeding rates. The powerful winds and jets generated by intense accretion heat up and disperse surrounding material, temporarily reducing the supply of fuel available for further growth. It's like a cosmic thermostat. The more vigorously a black hole feeds, the more it disrupts its own food supply. This creates episodic growth patterns throughout cosmic evolution. Periods of quiescence, during which the black hole sits relatively dormant, alternate with episodes of intense feeding when fresh material becomes available. These cycles can last millions or billions of years, creating the complex populations of active and dormant black holes we observe today. A critical mass of approximately 1,000 solar masses marks a transition point where gravitational effects begin to dominate the dynamics of entire stellar clusters. Above this threshold, black holes can gravitationally migrate toward the centers of dense stellar environments through dynamical friction, interactions with surrounding stars that cause the black hole to lose orbital energy and spiral inward. This hierarchical growth process means that larger black holes tend to grow even more rapidly, accumulating mass exponentially with time. The rich get richer in the cosmic economy, with the most massive black holes having the greatest capacity to capture additional material and merge with other black holes. Success breeds success on astronomical scales. The largest intermediate black holes approach masses of tens of thousands of suns, reaching the borderland where they begin to influence not just individual stars, but the collective behavior of stellar populations across regions spanning hundreds of light years. They become cosmic architects, shaping the very environments that created them. This intermediate phase establishes the foundations for understanding how the true titans emerge, the supermassive black holes that will dominate galactic centers and grow to masses billions of times greater than our Sun, reshaping the evolution of entire galaxies in the process. And when we step into the realm of these galactic giants, we enter a domain where individual objects contain between 1 million and 10 billion solar masses, gravitationally dominating the nuclei of virtually every galaxy we can observe throughout the cosmos. Supermassive black holes represent the ultimate expression of gravitational dominance on galactic scales. These cosmic titans sit at the centers of galaxies like ancient kings ruling over stellar empires, their gravitational influence extending across distances that dwarf everything we've discussed so far. To understand their true scale, let's begin with the supermassive black hole that governs our own cosmic neighborhood. Sagittarius A, the supermassive black hole at the center of our Milky Way, contains 1 million times the mass of our Sun, concentrated within an event horizon smaller than Mercury's orbit around our star. Picture this: an object containing the mass of 4 million stars, each one a nuclear furnace in its own right, compressed into a space that would fit comfortably within the inner reaches of our solar system. The gravitational influence of Sagittarius A extends approximately to 5 light years in all directions, controlling the orbits of thousands of stars packed into this central region with densities millions of times greater than the stellar neighborhood around our Sun. These stars dance in a complex choreography, their paths determined entirely by the invisible gravitational conductor at the galactic center. Some stars in this central region complete their orbital dance in just 16 years, remarkably fast, considering they're orbiting an object 26,000 light-years away from us. At their closest approach, these stellar racehorses reach velocities of 4,750 miles per second, traveling so fast they could circle the Earth in under 2 hours. The gravitational forces required to accelerate stellar mass objects to such speeds demonstrate the awesome power concentrated at our galaxy's heart. One particular star, designated S2, provided astronomers with the first direct observational confirmation of relativistic time dilation predicted by Einstein's general relativity. Scientists measured S2's orbital period with nanosecond precision, detecting tiny changes in the passage of time as the star approached and receded from the black hole. During its maximum approach in 2018, S2 experienced measurable relativistic effects, validating Einstein's century-old predictions about the nature of spacetime. But Sagittarius A is relatively modest compared to some of the supermassive giants found in other galaxies. The Event Horizon Telescope made history by capturing the first direct image of a supermassive black hole's shadow, not our own galactic center, but the monster that lurks at the heart of the galaxy M87, located 53 million light-years away. M87's central black hole contains 6.5 billion solar masses and launches a jet of plasma at 99.5%, the speed of light across a distance of 5,000 light-years. To help you visualize this jet, if our entire solar system were the size of a coin, this jet would stretch across several city blocks. The power output of this cosmic blowtorch reaches 10⁴42 watts, equivalent to the energy of trillions of stars like our Sun radiating simultaneously for billions of years. Think about that number for a moment: trillions of stars. Our galaxy contains roughly 400 billion stars, so this single jet carries the power of multiple galaxies worth of stellar energy, all focused into a beam narrower than the width of our solar system, and traveling at nearly the ultimate speed limit of the universe. Supermassive black holes don't simply exist passively at galactic centers. They actively regulate galactic growth through energetic feedback mechanisms. When these giants become highly active, feeding voraciously on surrounding material, they heat up and disperse the gas that would otherwise form new stars. This creates a delicate balance between stellar birth and stellar starvation that has shaped galaxy evolution for billions of years. Astronomers have discovered a remarkable correlation called the M-sigma relation, which connects the mass of a galaxy's central black hole with the velocity dispersion of stars in the galaxy's central bulge. This relationship suggests that black holes and their host galaxies grow together in an intimate evolutionary dance, maintaining a roughly constant mass ratio of about 0.1%. One solar mass of black hole for every 1,000 solar masses of galactic stellar content. This correlation implies something profound. Somehow, the growth of supermassive black holes and the formation of their host galaxies are inextricably linked processes. The black hole influences its galaxy, and the galaxy influences its black hole in a cosmic feedback loop that operates over billions of years and distances spanning hundreds of thousands of light years. When galaxies collide and merge, an inevitable consequence of cosmic expansion and gravitational attraction, their central supermassive black holes eventually spiral toward each other in a process that makes stellar mass black hole mergers look gentle by comparison. The merger of two supermassive black holes containing billions of solar masses would release energy equivalent to 100 million supernovas exploding simultaneously. The gravitational waves from such cataclysmic events would be so powerful they'd be detectable by pulsar timing arrays across our entire galaxy, creating permanent memory effects in the fabric of space-time itself. These waves would carry information about the merger across cosmic distances, rippling through space for billions of years after the event. However, the merger of supermassive black holes presents unique challenges. The three-body problem in celestial mechanics makes some mergers impossible without the assistance of a third supermassive black hole to break orbital symmetry. In triple systems, gravitational interactions can eject one of the components at velocities of thousands of miles per second, creating rogue supermassive black holes wandering through intergalactic space. These gravitational kicks can completely eject supermassive black holes from their host galaxies, leaving orphaned galactic cores forever. Imagine a galaxy suddenly losing its central organizing principle, the very object that has regulated star formation and determined galactic structure for billions of years, suddenly hurled into the cosmic void. When supermassive black holes enter phases of extremely active feeding, they become quasars, among the most luminous objects in the universe. These cosmic lighthouses shine more brightly than entire galaxies containing trillions of stars, powered solely by matter falling into their gravitational embrace. The most luminous known quasar, J2157362, consumes the equivalent of one solar mass every single day, radiating energy equivalent to quadrillions of suns. Quasar accretion disks can reach temperatures of 180,000 degrees Fahrenheit, emitting intense ultraviolet radiation that ionizes gas across millions of light years. Doppler-broadened emission lines reveal material orbiting at 6,200 miles per second near the event horizons of these distant powerhouses, testament to the extreme gravitational environment surrounding these feeding giants. The golden age of quasar activity occurred between 1 and 3 billion years after the Big Bang, when galactic mergers were more frequent and abundant gas supplies fed the growing supermassive black holes. During this cosmic era, the universe blazed with the light of millions of quasars, each one marking the location of a feeding, supermassive black hole in the process of rapid growth. But supermassive black holes can also remain dormant for billions of years between feeding episodes. Our own Sagittarius A currently sits in a relatively quiet state, occasionally flickering as small amounts of material fall across its event horizon, but nothing like the spectacular light shows produced by actively feeding quasars. Evidence of past activity includes the Fermi bubbles, enormous gamma-ray structures extending 31,000 light-years above and below our galactic disk. These ghostly remnants indicate that our central black hole was an active quasar just 6 million years ago, practically yesterday in cosmic terms. During that period, Sagittarius A would have outshone every star in our galaxy combined. Numerical simulations reveal that asymmetric mergers can deliver gravitational kicks to the resulting supermassive black holes, creating recoil velocities of thousands of miles per second. Such kicks can completely eject supermassive black holes from their galaxies, creating wandering monsters drifting through the intergalactic medium. The search for these rogue supermassive black holes represents one of the most challenging frontiers in modern observational astronomy. Each supermassive black hole shapes galactic evolution through feedback cycles that balance star formation with gas heating across cosmic time. They are the conductors of galactic symphonies, determining when and where new stars can form, regulating the chemical evolution of their host galaxies, and ultimately controlling the distribution of matter across hundreds of thousands of light years. This phase establishes how individual objects can transcend stellar scales entirely, growing to influence structures spanning hundreds of thousands of light years and containing hundreds of billions of stars, setting the stage for encounters with the most extreme examples of gravitational concentration the universe has yet revealed. And at the absolute pinnacle of this cosmic hierarchy sits TON 618, currently holding the record as the most massive confirmed black hole in the observable universe, containing a staggering 66 billion solar masses, concentrated into a gravitational monster that defies every attempt at comprehension. To grasp the scale of TON 618, consider that its event horizon measures 1,300 astronomical units in radius. Remember, 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. This means TON 618's event horizon extends 120.9 billion miles from its center, making it larger than the distance between our Sun and Pluto, multiplied by 9. If this cosmic giant somehow replaced our Sun, its event horizon would completely engulf the orbits of every planet in our solar system, swallowing Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune with room to spare. The gravitational influence of this titan extends approximately 11,000 light-years in all directions, dominating regions comparable in size to entire nebular complexes. To put this in perspective, if you could somehow place TON 618 at the center of our local stellar neighborhood, its gravitational control would extend far beyond the nearest stars, encompassing thousands of stellar systems in its inexorable grip. Phoenix A represents another colossus in this exclusive club of hypergiants, containing 20 billion solar masses and anchoring the center of the Phoenix galaxy cluster, which contains thousands of individual galaxies. These cosmic metropolises of galaxies are themselves among the largest gravitationally bound structures in the universe, yet they bow to the gravitational supremacy of the supermassive black holes at their hearts. During their most active feeding phases, these hypergiants consume material equivalent to dozens of entire stars annually. Imagine the gravitational appetite required to swallow stellar mass amounts of material every few weeks. Not just gas and dust, but the equivalent of complete nuclear furnaces, each one containing the mass of our Sun, disappearing into these cosmic abysses at rates that challenge our understanding of accretion physics. The luminosity of TON 618 during its quasar phase reaches 410 to 40 watts, outshining our entire Milky Way galaxy by a factor of 11,000. Think about this for a moment. Our galaxy contains 400 billion stars, each one a nuclear reactor converting mass to energy. Yet this single object produces more light than 11,000 galaxies like ours combined. If TON 618 were placed at the center of our local group of galaxies, it would be visible from Earth as a brilliant star, despite being a black hole. The relativistic jets launched by these ultimate giants can extend for millions of light years, creating radiolobes larger than entire galaxy groups. Alcyone possesses the largest known radiolobes, extending an mind-boggling 16.3 million light-years through intergalactic space. To help you visualize this scale, if our entire Milky Way galaxy were shrunk down to the size of a quarter lying on a table, Alcyoneus's radiolobes would stretch across more than 500 feet. These jets carry magnetic energy equivalent to trillions of supernovas exploding simultaneously, but distributed over millions of years of continuous activity. The magnetic fields confined within these jets remain coherent across distances that challenge every known phenomenon in plasma physics. How magnetic field lines can maintain their structure and organization across such vast cosmic distances remains one of the great puzzles of astrophysics. Material ejected in these jets travels at 99.9% the speed of light, while maintaining perfect collimation for millions of light years without significant dispersion. This represents a level of precision and stability that seems almost impossible. Imagine firing a laser beam across the width of our galaxy and having it arrive at the other side still perfectly focused and aimed. The radiation pressure from these ultra-massive black holes can actually prevent additional matter from falling in through what's called the Eddington limit. Above this critical threshold, radiation winds blow away material faster than gravity can capture it for feeding. It's a cosmic speed limit for growth. The black hole's own brilliance becomes so intense that it literally pushes away its food supply. Some supermassive black holes temporarily violate this limit through super-Eddington accretion during episodes of catastrophic feeding, growing faster than theoretical models suggest should be possible. These violations might explain how some black holes achieved such enormous masses so early in cosmic history. When the universe should not have had enough time for such giants to grow through normal accretion processes, theoretical models suggest that black holes can grow to approximately 50 billion solar masses before limiting effects become dominant. Above this critical mass, the time required for additional accretion begins to exceed the current age of the universe, making further growth cosmologically impossible. We may be witnessing black holes that have approached the natural limits imposed by cosmic evolution and fuel availability. The distribution of observed black hole masses suggests we're approaching these fundamental boundaries. TON 618, at 66 billion solar masses, already exceeds some theoretical predictions for maximum possible size, hinting that our understanding of black hole growth remains incomplete or that special conditions allowed certain objects to surpass normal limits. Hypothetical primordial black holes formed during cosmic inflation could theoretically exceed all observational limits by enormous factors. If such objects exist, they would represent relics from the universe's first moments, when quantum fluctuations in the primordial density field could have collapsed directly into black holes without forming stars first. Simulations of hierarchical growth show that mergers of galaxy clusters could produce central black holes containing hundreds of billions of solar masses. Such monsters would exist only in the most massive galaxy clusters, gravitationally dominating structures spanning tens of millions of light years. These would be black holes large enough to influence the evolution of cosmic structure on the largest observable scales. A black hole containing 100 billion solar masses would have an event horizon measuring 2,000 astronomical units in radius, large enough to comfortably contain multiple complete solar systems. The space-time curvature near such objects would be so extreme that stable orbits could exist only at distances of several light years, farther than the distance to our nearest stellar neighbor. Paradoxically, material falling into these ultimate giants would experience such gentle tidal gradients that macroscopic objects could cross the event horizon practically intact initially. The event horizon would be so vast that the gravitational field would vary only slightly across human-scale distances, making the crossing almost imperceptible from the perspective of an infalling observer. Here's something that seems to defy intuition. Larger black holes actually have lower average density near their event horizons. A black hole containing 1 trillion solar masses would have an average density lower than the air you're breathing right now. This counterintuitive inversion demonstrates how extreme scale breaks down analogies based on everyday experience with density and material compactness. The largest observed black holes represent approximately 1% of their host galaxies' total mass, concentrated into regions smaller than our solar system. This ratio suggests a fundamental relationship between galaxy formation and black hole growth that operates across cosmic time, with supermassive black holes serving as both products and architects of galactic evolution. These giants establish the observational upper limits for individual objects in our universe, raising profound questions about whether fundamental physical limitations constrain the maximum possible concentration of matter and energy. And as we push against these boundaries, we discover that the laws of physics themselves begin to impose restrictions on how large black holes can grow, based on the finite age of our universe and the fundamental availability of material to feed these cosmic giants. The physics of black hole growth reveals inherent constraints that operate on cosmic timescales. The Salpeter time represents the minimum period required to double a black hole's mass through efficient accretion, approximately 45 million years. This timescale emerges from the fundamental balance between gravitational attraction and radiation pressure, setting a cosmic speed limit on how quickly these objects can grow, even under ideal conditions. Even with continuous accretion at the Eddington limit, the maximum rate at which matter can fall into a black hole before radiation pressure blows away the fuel supply, black holes would require billions of years to reach the extreme masses we observe. A seed black hole containing 100 solar masses at redshift Z120, when the universe was very young, could grow to at most 1 billion solar masses by the present day through this standard accretion process. But here's where observations challenge our theoretical understanding. Astronomers have discovered quasars containing billions of solar masses just 800 million years after the Big Bang. These early cosmic giants shouldn't exist according to standard growth models. There simply hasn't been enough time for normal accretion processes to build such massive objects from stellar mass seeds. Explaining these observationally confirmed early giants requires either temporary super-Eddington accretion or much more massive initial seeds than stellar collapse can provide. Perhaps the early universe experienced conditions that allowed black holes to violate normal growth limits, or maybe direct collapse of primordial gas clouds created heavy seeds containing thousands of solar masses from the beginning. A fundamental cosmological limit emerges when a black hole's Schwarzschild radius approaches the Hubble horizon, the boundary of our observable universe. A black hole with a mass of approximately 10 to 23 solar masses would have an event horizon comparable to the radius of the observable universe itself. Such an object would transcend the distinction between interior and exterior, potentially suggesting that our observable universe might itself be the interior of a supermassive black hole. The entropy of black holes, described by the Bekenstein-Hawking formula, scales with the area of the event horizon, rather than its volume. This suggests fundamental informational limits for macroscopic objects. Maximum black holes would contain approximately 10^123 bits of information, approaching the theoretical maximum entropy possible in any observable region of space. Hawking temperature decreases inversely with mass, making the largest black holes colder than the cosmic microwave background radiation that fills intergalactic space. Tonna 618 possesses a Hawking temperature of merely 1.8 Kelvin, that's negative 459.67 degrees Fahrenheit, trillions of times colder than the already frigid 2.7 Kelvin temperature of deep space. These cosmic giants radiate energy so slowly through Hawking radiation that they would require 10^100 years to evaporate completely, a time span so vast it extends far beyond the heat death of the universe itself. For comparison, if the current age of the universe were compressed into a single second, these black holes would continue radiating for longer than the age of the universe, repeated a trillion times over. The information paradox questions whether information that falls into black holes is preserved or destroyed during Hawking evaporation. If information is truly lost, it would violate one of the most fundamental principles of quantum mechanics: that information must be conserved in all physical processes. This creates a deep conflict between general relativity and quantum theory at the heart of black hole physics. Some physicists propose firewall solutions, suggesting that black hole horizons might be destructive interfaces that annihilate quantum information instantaneously. From this perspective, the smooth spacetime predicted by Einstein's theory might be an illusion, with the event horizon actually being a wall of high-energy particles that destroys anything attempting to cross. Alternative approaches like holographic correspondence propose that all information falling into a black hole is encoded redundantly on the two-dimensional surface of the event horizon. In this view, the three-dimensional interior of a black hole might be an emergent phenomenon, with all the real physics happening on the horizon boundary. The quantum complementarity conjecture suggests that internal and external observers experience mutually inconsistent but individually valid physical realities. An outside observer would see information preserved on the horizon surface, while an infalling observer would experience passage through empty space. Two descriptions that seem contradictory but might both be correct within their respective reference frames. Quantum tidal effects near singularities might create energy fluctuations that prevent the formation of mathematically infinite curvatures. Rather than true singularities with infinite density, quantum mechanics might smooth out these extreme regions, replacing mathematical infinities with finite but extremely large values. Loop quantum gravity proposes that singularities are replaced by quantum bounces that connect black holes to baby universes. In this picture, what appears to be the ultimate endpoint of gravitational collapse actually becomes a bridge to new space-time regions, with matter emerging into newly created cosmic domains. String theory suggests that extremely massive black holes might transition into exotic objects called fuzzballs, extended structures without well-defined event horizons. These objects would look like black holes from a distance, but would have fundamentally different internal structure, potentially resolving paradoxes about information loss and singularity formation. The Planck scale imposes a fundamental limit, where classical geometry loses meaning, potentially resolving paradoxes about central singularities. Below distances of 10 to the 35 meters and timescales of 10 to the 43 seconds, space and time themselves might become discrete and granular rather than smooth and continuous. Quantum fluctuations of the vacuum near event horizons might amplify gravitationally, creating instabilities that limit maximum possible masses. These effects could provide natural cutoffs that prevent black holes from growing beyond certain theoretical limits, even when abundant fuel supplies are available. Dark energy, which dominates the current expansion of our universe, reduces the efficiency of future accretion by making matter more diffuse and harder to capture. As cosmic expansion accelerates, black holes will find it increasingly difficult to gather additional material, effectively starving the giants we observe today. Quintessence models suggest that dark energy might accelerate Hawking evaporation, potentially reducing black hole lifetimes below the enormous values predicted by standard theory. If dark energy interacts with black holes in unexpected ways, even the largest giants might not be as eternal as we currently believe. In universes with slightly different fundamental constants, black holes might dominate completely over normal matter from the earliest epochs. The delicate balance that allows stars, planets, and life to exist depends critically on precise values of constants, like the fine structure constant and the strength of gravitational coupling. The stability of black holes themselves depends on these fundamental constants maintaining their observed values. Minimal variations could result in universes where black holes either evaporate instantaneously or grow without any limiting mechanisms, creating cosmic environments completely unlike our own. The anthropic principle suggests that we observe these specific values because only they permit the existence of complex observers like ourselves. In a multiverse of possibilities, we necessarily find ourselves in a universe where the constants allow both stable matter and stable black holes to coexist. These theoretical limits establish conceptual boundaries where known physics encounters fundamental questions about the nature of reality itself. And when we contemplate the largest black holes known to science, we find ourselves forced to reconceptualize our most basic notions about size, distance, and the very meaning of scale in a universe that operates according to principles that completely transcend familiar experience. The largest known black holes transcend every attempt at intuitive understanding, demolishing the scaffolding of analogies we use to make sense of cosmic scales. Consider TON 6-18. If we could somehow shrink this 66 billion solar mass giant down to the size of a basketball sitting on your kitchen table, our entire Earth would become smaller than a proton. Not smaller than an atom, not smaller than a cell, but smaller than a single subatomic particle, one of the fundamental building blocks of matter itself. Even more remarkably, if you could hold our entire Milky Way galaxy in the palm of your hand like a delicate cosmic snow globe, the event horizon of TON 6-18 would still measure several yards across. Our galaxy, with its 400 billion stars spanning 100,000 light-years compressed to handheld size, would still be dwarfed by the event horizon of this single object. The gravitational influence of Phoenix Aetos extends across distances comparable to the space between our galaxy and Andromeda, our nearest major galactic neighbor. That's 2.5 million light-years of gravitational control, a sphere of influence so vast that dozens of galaxies like our own could fit comfortably within its domain. This isn't just gravitational attraction, it's architectural control over cosmic structure on scales that encompass entire galaxy clusters. Material orbiting close to TON 6-18's event horizon completes one orbit in approximately 40 Earth days, surprisingly slow for such a massive object. But this apparent sluggishness reflects the enormous circumference that matter must traverse. The orbital velocity required to maintain the last stable orbit reaches 62,000 miles per second, fully one-third the speed of light. At such velocities, relativistic effects become dominant, and the very concepts of space and time begin to stretch and distort. A beam of light would require 3.7 hours to travel from one side of TON 618's event horizon to the other. Think about that journey. Light, traveling at 186,000 miles per second, takes longer to cross this object's boundary than it takes you to watch a movie. If you could somehow observe this black hole from a safe distance, it would appear as a dark disk larger than our Sun appears from Earth, despite being billions of times more distant. The space-time curvature around these giants becomes so extreme that light passing nearby bends at angles exceeding 90 degrees, creating multiple images of the same distant objects. These gravitational lenses can focus light from galaxies millions of light years away, creating natural gravitational telescopes with magnification factors reaching millions of times, more powerful than any instrument humanity could ever hope to build. The gravitational field alters time so drastically that clocks near the event horizon would run trillions of times slower than clocks in normal space. An astronaut orbiting close to TON 619's horizon would experience only minutes while billions of years pass in the rest of the universe. This extreme time dilation means that regions near the largest black holes evolve in cosmic slow motion relative to everything else. To comprehend the energy scales involved, consider that the gravitational binding energy of TON 6 equals approximately 3% of its total mass converted to pure energy according to Einstein's E-2. This binding energy corresponds to the total energy output of 100 trillion stars, like our Sun radiating continuously for their entire 10 billion-year lifespans. If this energy were released instantaneously, the explosion would be visible across half the observable universe as the most luminous event physically possible. The information content stored on TON 618's event horizon would be sufficient to describe the position and momentum of every single particle in volumes comparable to entire galaxies. Processing this information would require quantum computers with more qubits than there are atoms in millions of galaxies like our own. The computational requirements transcend not just current technology but any conceivable future technology based on matter as we understand it. The thermodynamic entropy of this single black hole exceeds the combined entropy of all the stars in our local supercluster, Laniakea, which contains over 100,000 galaxies. This represents the ultimate concentration of disorder and information packed into a region that, while enormous by stellar standards, remains microscopically small compared to the cosmic structures it influences. Paradoxically, despite its colossal mass, the average density near TON 618's event horizon is actually lower than the density of Earth's atmosphere. This counterintuitive result emerges because density scales as mass divided by volume, and volume grows as the cube of radius, while mass only scales linearly. A human-sized object could theoretically cross the event horizon without being immediately shredded by tidal forces. The subjective experience of falling into such a giant would be remarkably gentle initially, normal free fall, until approaching the central singularity, where tidal effects would finally dominate. But from an external perspective, that same falling object would appear to freeze forever at the horizon surface, its image redshifting until it fades from view. This duality of perspective demonstrates how extreme black holes shatter intuitive notions about simultaneity and shared objective reality. The relativistic jets from ultramassive black holes carry enough energy to heat intergalactic gas throughout entire cosmic web filaments. These jets can suppress star formation across regions larger than galaxy groups, actively sculpting the evolution of cosmic structure on scales spanning hundreds of millions of light years. They serve as cosmic thermostats, regulating when and where new stars can form across vast cosmic territories. Computer simulations reveal that without supermassive black holes, our universe would contain 10 times more stars distributed in gigantic, gravitationally unstable galaxies. These gravitational regulators maintain a delicate balance between star formation and gas heating across scales of hundreds of millions of light years, essentially governing the cosmic economy of matter conversion and energy distribution. The very existence of ultramassive black holes implies that the hierarchical structuring of our universe possesses well-defined natural upper limits. Beyond certain mass scales, even black holes cannot grow larger within cosmic time constraints and fuel availability. We may be witnessing the maximum concentration of matter that our universe's physical laws permit within its current age and expansion rate. These cosmic giants represent concentrations so extreme that they challenge the fundamental categories we use to classify objects. Are they still objects in any meaningful sense, or have they become phenomena that define the geometric properties of spacetime itself across entire cosmic regions? At what point does an object become so massive and influential that it transcends classification as a thing and becomes instead a feature of reality's basic architecture? We have reached the apex of the cosmic scale, where individual entities transcend classification as mere objects and transform into phenomena that fundamentally define the space-time geometry of entire cosmic regions. And confronting the scale of these largest black holes forces a radical recalibration of our understanding about humanity's place in the cosmos, compelling us to grapple with questions that reach far beyond astronomy into the very heart of what it means to exist as conscious beings in an universe of such incomprehensible magnitude. The total mass of every human being who has ever lived, from our earliest ancestors to every person alive today, equals approximately a grain of sand when compared to Ton 618. Every thought ever conceived, every emotion ever felt, every dream ever pursued by our entire species represents a collective mass so infinitesimally small that it wouldn't register even the tiniest fluctuation in this cosmic giant's behavior or gravitational field. Consider this perspective for a moment. All the love letters ever written, all the scientific discoveries ever made, all the music ever composed, every moment of joy and every tear of sorrow in human history. The combined physical mass of every brain that produced these experiences amounts to less than a speck of dust in relation to this single cosmic entity. Our entire civilization could be annihilated. Every city, every monument, every accumulated work of art and science, every record of human achievement, and these cosmic titans wouldn't register even the slightest detectable change in their mass or gravitational influence. The complete elimination of our planet, our solar system, even our local stellar neighborhood containing hundreds of stars would be less than a rounding error in the cosmic ledger kept by objects like Ton 618. If the entire local group of galaxies, including the Milky Way, Andromeda, and dozens of smaller galaxies spanning 10 million light-years, were to vanish instantly, Ton 618 would continue its cosmic dance completely unchanged, unaware that billions upon billions of stars and countless potential civilizations had simply ceased to exist. The time required for light to traverse Ton 618's event horizon, those 7 hours we discussed earlier, exceeds the entire span from the first written records of human civilization to the present day. Think about what this means in terms of lived experience. Events occurring simultaneously on opposite sides of this black hole's horizon are separated by temporal intervals greater than the span from the first Sumerian cuneiform tablets to your reading of these words. If two photons began their journey across this horizon at the same moment, one starting from the left side and one from the right, the time difference between their arrivals would encompass the rise and fall of every empire in human history. The energy contained within TON 618 staggers comprehension. This single object could supply all of Earth's energy needs for 10-30 years. That's not millions or billions of years, but a number with 30 zeros after it, a time span so vast that if you wrote out each year individually, the resulting number would contain more digits than there are atoms in your body, more digits than there are stars in our galaxy. Even extracting just 0.01% of this energy through theoretical Penrose processes would power our entire civilization until the heat death of the universe itself, long after every star has burned out and space has expanded beyond the possibility of new star formation. Yet here lies the cruel irony. Actually reaching such an object to harness this energy transcends any conceivable technological capability. The journey to TON 618, located billions of light years away, would require millions of human generations traveling at maximum theoretically possible velocities for spacecraft, perhaps 10% of light speed using fusion ramjets or antimatter propulsion systems that remain purely theoretical. During such an epic voyage spanning millions of years, our species would likely evolve beyond recognition multiple times, face extinction events, develop entirely new forms of consciousness, or transform into something that bears no resemblance to the humans who began the journey. The destination we set out to reach would be achieved, if at all, by beings who might not even qualify as recognizably human anymore. Here's a paradox that completely defies terrestrial intuition. The larger the black hole, the safer it becomes for close observation. The tidal gradients that would instantly shred any material object near a stellar mass black hole become remarkably gentle near giants like TON 618. An astronaut could orbit comfortably at distances where smaller black holes would tear apart atomic nuclei themselves. You could theoretically pilot a spacecraft closer to TON 618's event horizon than you could approach a black hole with the mass of our Sun and experience less stress on your body than you feel during a commercial airline flight. This counterintuitive inversion illustrates how extreme scale subverts every expectation based on terrestrial experience with massive objects. Supermassive black holes function as the fundamental atoms of large-scale cosmic structure, organizing matter into the hierarchical patterns we observe throughout the universe. Without these gravitational architects, computer simulations show that the cosmos would be a homogeneous chaos lacking the complex structures necessary for the emergence of life. Instead of the beautiful cosmic web of galaxies, clusters, and filaments we observe today, we would have a universe filled with enormous, unstable, galaxy-like structures containing 10 times more stars, but lacking the gravitational regulation needed to maintain stable planetary systems over billions of years. The existence of conscious observers like us depends fundamentally on the prior existence of these giants that structure galactic formation. We are literally byproducts of supermassive black hole evolution. Our very ability to contemplate these objects emerges from cosmic processes they themselves initiated billions of years ago when the universe was young and chaotic. The heavy elements in your body were synthesized in stellar cores that orbited around growing supermassive black holes, experienced their gravitational influence, and eventually distributed these life-essential materials across space through supernova explosions regulated by black hole feedback mechanisms. This cosmic dependency suggests that consciousness and extreme black holes represent complementary aspects of universes capable of sustaining complexity. Perhaps the universe requires both maximal gravitational concentration and maximal informational processing. the unconscious giants that shape space and time through pure gravitational force, and the conscious observers who can comprehend their meaning through abstract thought and mathematical reasoning. The statistical rarity of conditions necessary to produce conscious observers makes every moment of contemplation infinitely precious in a literal sense. You might be among the only beings in the local universe, perhaps within millions of light years, capable of understanding and appreciating these extreme objects through mathematical reasoning and abstract thought. Your capacity to think about TON 618, to visualize its scale, to comprehend its implications, represents an almost miraculous convergence of cosmic evolution spanning 13.8 billion years of universal history. Consider the extraordinary achievement this represents. Through theoretical physics developed over just the past few centuries, creatures of utterly negligible mass can understand objects trillions of times more massive than themselves. Your brain, weighing roughly 3 pounds and consuming about 20 watts of power, can model and comprehend entities containing the mass of 66 billion stars and radiating more energy than thousands of galaxies. This represents a cognitive achievement that may be unique in our cosmic neighborhood, a triumph of evolved intelligence over the limitations of physical scale. This disproportionality suggests that informational complexity might be more fundamentally important than mass or energy in the cosmic hierarchy of significance. Black holes represent maximum possible information storage in defined spatial regions according to the holographic principle, containing approximately 10^123 bits of data encoded on their event horizon surfaces, but they lack any capacity to process this information consciously. They are cosmic libraries containing unimaginable amounts of data about every particle that has ever fallen past their event horizons, but with no librarian to read the books, no consciousness to interpret the meaning. Human brains, conversely, process information qualitatively rather than quantitatively, creating subjective experiences, emotional responses, aesthetic appreciation, and conceptual understanding of objective reality. While a black hole might store vastly more raw information, only conscious minds can transform information into knowledge, knowledge into wisdom, and facts into meaning. The simultaneous existence of maximum information processors, black holes, and qualitative information processors, conscious minds, suggests a fundamental complementarity in cosmic architecture. The universe seems to require both unconscious maximization of information storage and conscious interpretation of information's meaning, raw data preservation, and meaningful understanding working together across impossible scales of space and time. Your ability to comprehend black holes through mathematical theories demonstrates conclusively that physical size doesn't determine ontological significance. The smallest entities, thoughts, equations, insights, moments of understanding, can encompass and explain the largest phenomena in existence. A single equation written in a few lines can describe objects larger than solar systems, predict their behavior across billions of years, and reveal deep truths about the nature of space, time, and gravity that apply throughout the cosmos. The same primordial density fluctuations in the early universe that eventually evolved into supermassive black holes also led to the formation of the first stars, the first planets, and ultimately to the chemical elements and gravitational conditions that made conscious observers like yourself possible. This common origin implies that we exist in a profoundly interconnected universe, where extreme scales are mutually dependent rather than separate phenomena operating according to different principles. We share cosmic ancestry with the very objects that seem to dwarf us into complete insignificance. The carbon in your body, the oxygen you breathe, the iron in your blood, the calcium in your bones, all were forged in stellar cores that eventually contributed to the formation of both black holes and biological complexity. You are made of star stuff that danced around these cosmic giants for billions of years before eventually finding its way into the molecular machinery that enables your consciousness. Every breath you take connects you to this vast cosmic story, spanning billions of years and trillions of miles. The atoms cycling through your lungs have traveled across light years of space, participated in countless stellar generations, witnessed the birth and death of solar systems, and observed the growth of supermassive black holes from modest beginnings to cosmic dominance. You are not separate from this universe. You are one of its most remarkable expressions, a temporary arrangement of cosmic matter that has somehow achieved the ability to contemplate its own origins and destiny. Contemplating the largest black holes doesn't diminish human significance. It reveals our participation in a cosmic drama of incomparable complexity and beauty. And as we step back from this extraordinary journey through scales that span from microscopic quantum realms to cosmic phenomena larger than solar systems, we discover that our exploration of black holes has revealed something profound about the nature of size and significance. They operate according to completely different logical frameworks in our universe. Our journey began with objects smaller than coins yet containing the mass of entire mountain ranges, and we conclude with event horizons larger than the orbits of planets, spanning distances that dwarf our solar system. This progression across 60 orders of magnitude demonstrates that nature operates according to scales that fundamentally transcend the intuition developed by creatures who evolved to navigate environments measured in feet, miles, and human lifespans. Our brains, shaped by evolutionary pressures to understand falling rocks and running prey, find themselves confronting objects that challenge every assumption about how reality should behave. Each category of black hole has taught us something different about the absolute limits of physics, from quantum mechanics operating at microscopic scales to relativistic cosmology governing the largest structures in the observable universe. The smallest theoretical black holes revealed deep tensions between gravity and quantum mechanics that physicists still struggle to reconcile satisfactorily. These tensions suggest that our two most successful theories, general relativity and quantum field theory, remain fundamentally incomplete, pointing toward new physics that awaits discovery. Stellar mass black holes demonstrated how matter can collapse beyond any possible resistance, creating regions from which information can never return to the external universe. They showed us that the universe contains points of no return built into its fundamental architecture, boundaries beyond which cause and effect operate according to different rules than anything in our terrestrial experience. These objects forced us to confront the reality that information itself might have physical limitations, that there exist cosmic delete buttons capable of erasing data from reality permanently. Intermediate mass black holes revealed how hierarchical growth connects individual stellar scales with collective galactic dynamics through successive mergers spanning millions of years. They represent the adolescent phase of black hole evolution, demonstrating how cosmic structures grow through accretion and collision rather than simple accumulation. These objects bridge the gap between stellar death and galactic architecture, showing us that the universe builds complexity through violent encounters that destroy individual components while creating larger, more influential entities. Supermassive black holes revealed that these objects transcend their role as mere things to become fundamental architects of cosmic structure itself. They regulate star formation across hundreds of thousands of light years, determine the chemical evolution of entire galaxies, and orchestrate the distribution of matter on scales so vast they influence the observable properties of the cosmic web. These giants forced us to recognize that individual objects can grow large enough to become environmental factors rather than simple participants in cosmic evolution. The largest giants compelled recognition that we have approached natural limits imposed by the finite age and accelerating expansion of our universe. Objects like TON 618 may represent the maximum concentration of matter that cosmological evolution can produce within the time available since the Big Bang. They exist at the intersection of possibility and impossibility, having grown as large as physical law permits within cosmic history's constraints. Paradoxically, we discovered that larger black holes possess gentler local curvature and would be safer to approach than their smaller counterparts. This counterintuitive finding completely subverts expectations based on terrestrial analogies, where larger typically correlates with more dangerous or more extreme. A black hole containing billions of solar masses creates a more benign environment near its event horizon than one containing just a few stellar masses, the ultimate demonstration of how extreme scale breaks down familiar categories. The discovery that average density decreases with increasing mass illustrated how extreme scale shatters all familiar conceptual frameworks. The largest black holes have average densities lower than the air you breathe, despite containing masses equivalent to billions of stars. This inversion of intuitive relationships between size, mass, and density forces us to abandon terrestrial analogies when contemplating cosmic extremes. Black holes function as natural laboratories where fundamental physics is tested under conditions impossible to reproduce in any terrestrial experiment. They create gravitational fields billions of times stronger than anything achievable on Earth, temperatures both infinitely hot and infinitely cold, and space-time curvatures that approach mathematical limits. These objects serve as cosmic testing grounds where our theories either succeed spectacularly or fail dramatically, providing crucial data about physical law under the most extreme conditions possible. The detection of gravitational waves from black hole mergers confirmed Einstein's century-old predictions with extraordinary precision, validating theoretical understanding through direct experimental observation. When LIGO detected the ripples in spacetime caused by colliding black holes, it represented one of the greatest triumphs in the history of science, the confirmation of phenomena so subtle they require instruments capable of measuring distortions smaller than 1/10,000th the width of a proton across the distances of several miles. The first image captured by the Event Horizon Telescope transformed abstract mathematical concepts into concrete visual reality, making the event horizon something we could actually see rather than merely calculate. That photograph of M87's central black hole represented more than just a technical achievement. It made tangible something that had existed only in equations and computer simulations, providing visual proof that our mathematical descriptions of these extreme objects correspond to observable reality. These observational confirmations demonstrate the extraordinary power of mathematics to describe the most extreme aspects of physical reality accurately. The fact that equations written by humans sitting in quiet offices can predict the behavior of objects containing billions of stellar masses across cosmological distances represents one of the most remarkable achievements in intellectual history. Mathematics, apparently invented by minds that evolved to count berries and track seasons, turns out to describe cosmic phenomena with precision that approaches perfection. Yet simultaneously, persistent paradoxes like the information problem indicate that our current understanding remains fundamentally incomplete despite these successes. The conflict between quantum mechanics and general relativity that emerges most clearly in black hole physics suggests that both theories are approximations to some deeper truth we haven't yet discovered. Black holes serve as cosmic Rosetta Stones containing clues about the ultimate nature of reality written in a language we're still learning to read. The tension between general relativity and quantum mechanics suggests that black holes guard secrets about the deeper nature of physical law that we haven't yet accessed. These objects exist precisely where our two most successful theories make contradictory predictions, forcing us to confront the reality that our understanding of space, time, matter, and energy remains incomplete. They are cosmic question marks, challenging us to develop new physics that can reconcile quantum discreteness with gravitational continuity. Emerging theories like loop quantum gravity and string theory offer possible resolutions through completely novel physics that transcends current frameworks. These speculative approaches suggest that spacetime itself might be quantized at the smallest scales, that black holes might connect to other universes, or that reality possesses hidden dimensions we cannot directly perceive. Whether any of these ideas prove correct, they illustrate how black holes continue to drive theoretical innovation and force us to question fundamental assumptions about reality's architecture. Regardless of future theoretical developments, black holes have already permanently transformed our understanding of space, time, and causality. They forced recognition that time is not absolute, but can be dilated, stretched, and even stopped relative to distant observers. They demonstrated that space itself can be curved, twisted, and dragged by massive objects. They revealed that information might be fundamentally limited rather than infinitely preservable, and that the universe contains regions where normal concepts of cause and effect break down completely. These lessons transcend astronomy to influence philosophy, forcing us to question basic assumptions about the nature of objective reality itself. If time can slow down and space can be curved, if information can be lost and causality can be violated, then what does this mean for our understanding of existence, consciousness, and meaning? Black holes challenge not just our scientific theories, but our philosophical frameworks for making sense of reality and our place within it. The discovery that we are literally constructed from material forged in stellar cores that eventually contributed to black hole formation creates an intimate connection between life and these cosmic extremes. The carbon in your body, the iron in your blood, and the calcium in your bones originated in nuclear furnaces that operated under the gravitational influence of growing black holes. This cosmic genealogy means that when you contemplate black holes, you're using atoms that share common ancestry with these gravitational giants. Your capacity to understand objects trillions of times more massive than yourself through abstract thought represents an extraordinary cognitive achievement that may be unique in our cosmic neighborhood. We have developed mathematical tools capable of describing precisely phenomena completely outside the domain of direct sensory experience. The human mind, evolved to navigate environments of trees and rivers, can somehow comprehend objects larger than solar systems and events spanning billions of years. This conceptual transcendence suggests that conscious minds might be among the most remarkable phenomena in the known universe, regardless of their physical scale. While black holes represent the extreme limits of passive physical complexity, maximum information storage without consciousness, minds represent the emergence of active, self-aware complexity that can comprehend its own existence and place in the cosmic order. The coexistence of these two types of complexity in the same universe hints at possibilities for deep connections we have not yet comprehended. And after contemplating the extreme scales of the largest black holes, we inevitably return to the fundamental question about our place in this vast cosmic architecture, a question that becomes more profound and paradoxical the deeper we venture into the realm of these gravitational giants. Physically, we are absolutely insignificant, less than subatomic particles when measured against the scale of the cosmic giants we have explored throughout this journey. If TON 618 were scaled down to the size of Earth, every human who has ever lived would collectively represent less mass than a single electron. Our entire solar system, with all its planets, moons, and asteroids, would be smaller than the nucleus of a hydrogen atom. The complete physical insignificance is so extreme that it challenges our ability to find adequate comparisons from everyday experience. Every mountain range, every ocean, every cloud formation that has ever existed on Earth represents less material than the smallest detectable fluctuation in a supermassive black hole's mass. The combined weight of every living creature that has ever existed, every dinosaur, every whale, every microscopic organism, amounts to less than a grain of cosmic dust when compared to objects like Ton 618. Our physical presence in the universe is so negligible that it approaches mathematical zero. Yet cognitively, we are extraordinary beyond measure, possessing the unique capacity to understand and mathematically model these objects through abstract thought processes that seem to defy physical explanation. Your brain, weighing roughly 3 pounds and consuming about 20 watts of power, less energy than a dim light bulb, can comprehend entities containing 66 billion solar masses and spanning distances larger than our solar system. This cognitive achievement represents a triumph that may be unparalleled in our cosmic neighborhood. Consider what this actually means in practical terms. A biological computer that could fit in your hands and runs on the energy equivalent of a small appliance can model the behavior of objects millions of light years away, predict their gravitational effects across cosmic time, and understand phenomena operating under physical conditions that would instantly destroy any material substance we know. This represents computational efficiency and conceptual power that transcends any technological achievement in human history. This duality, physical insignificance combined with cognitive significance, defines the central paradox of conscious human existence in a universe of extremes. We exist as conscious specks capable of contemplating infinities, as temporary arrangements of matter that have somehow achieved the ability to understand their own cosmic context. This paradox suggests something profound about the nature of complexity, information, and meaning in a universe that seems structured to produce both maximum gravitational concentration and maximum cognitive sophistication. Black holes exist as the universe's maximum information processors, purely passive entities that concentrate data without any capacity for interpretation, understanding, or conscious experience. They store every bit of information about every particle that has ever crossed their event horizons, maintaining perfect records encoded on their surfaces according to the holographic principle. A black hole like Ton 618 contains approximately 10^123 bits of information, more data than exists in all the libraries, computers, and storage devices ever created by human civilization combined. Yet, for all their information content, black holes remain fundamentally unconscious, lacking any mechanism to process, interpret, or derive meaning from the vast libraries of data they contain. They are cosmic hard drives without operating systems, infinite databases without query capabilities, perfect memories without consciousness to access the stored experiences. Human minds, conversely, process information qualitatively rather than quantitatively, creating meaning, beauty, emotional depth, and conceptual understanding from the limited sensory data available to biological organisms. While a black hole might store vastly more raw information than any human brain, only conscious minds can transform mere information into knowledge, knowledge into wisdom, facts into insights, and observations into genuine understanding of cosmic significance and beauty. Your brain processes perhaps 1016 operations per second, orders of magnitude less than advanced supercomputers, yet it achieves something no computer has ever accomplished. It creates subjective experience, aesthetic appreciation, and genuine understanding of concepts like infinity, beauty, and meaning. the qualitative processing performed by consciousness appears to be fundamentally different from any quantitative information manipulation, no matter how sophisticated. We represent the improbable emergence of a universe that has developed the capacity to observe itself, question its own nature, and comprehend its most extreme structures through mathematical abstraction. The statistical probability of conscious observers existing in a universe dominated by unconscious objects, stars, planets, black holes, and vast expanses of empty space, is astronomically small. The precise fine-tuning of physical constants required to produce stable atoms, stellar nucleosynthesis, planetary formation, and biological complexity represents a convergence of factors so unlikely it approaches impossibility. This makes every moment of consciousness and every scientific discovery an event of immeasurable cosmic significance, regardless of the physical scales involved. When you understand something new about black holes, when you grasp a concept that seemed impossible moments before, when you experience that sudden flash of comprehension, these cognitive events represent victories of conscious complexity over unconscious simplicity that may be among the rarest phenomena in the observable universe. Your capacity to contemplate TON 618 and understand its properties represents a triumph of emergent complexity over gravitational simplicity that spans 8 billion years of cosmic evolution. While that black hole reduces all complexity to 3 simple parameters, mass, charge, and rotation, your mind creates rich experiences, emotional responses, aesthetic appreciation, and conceptual frameworks from simple neural interactions. The contrast could not be more stark or more cosmically significant. Black holes represent the ultimate destinations of matter, endpoints where all the diversity and complexity of the material world gets reduced to fundamental gravitational entities described by just a few numbers. No matter what falls past an event horizon, whether it's a hydrogen atom, a complete library, a work of art, or a living organism, all information about internal structure becomes inaccessible to the external universe. Complexity gets erased, diversity gets eliminated, and only the most basic gravitational properties remain. Conscious minds, however, represent the ultimate destinations of organized information, endpoints where simple physical processes somehow give rise to subjective experience, self-awareness, and the capacity for abstract thought about cosmic scales and meaning. Neural networks containing nothing more exotic than carbon, hydrogen, oxygen, and a few trace elements somehow produce phenomena like self-awareness, mathematical insight, aesthetic appreciation, and the capacity to contemplate their own existence and place in cosmic history. The simultaneous existence of both phenomena suggests that our universe operates through a fundamental complementarity between maximum simplicity and maximum complexity. On one side, we have gravitational collapse that reduces everything to its simplest possible form. On the other side, we have biological and cognitive evolution that builds complexity upon complexity, creating systems capable of self-reflection and cosmic understanding. Black holes simplify matter to the maximum extreme possible, reducing all the rich diversity of atoms, molecules, and structures to just mass, electric charge, and rotational momentum. Consciousness, conversely, complexifies information to the maximum degree possible, creating rich subjective experiences from relatively simple patterns of neural activity. These opposing tendencies might both be necessary for a universe capable of sustaining organized complexity over cosmic timescales. This polar opposition suggests that we have evolved in a universe specifically structured to produce both extremes of simplicity and extremes of complexity operating simultaneously. Rather than being accidents or side effects, both black holes and conscious minds might represent necessary features of any universe capable of sustaining organized complexity over billions of years. They might be complementary aspects of cosmic architecture rather than independent phenomena. Your existence as a conscious observer might be as fundamental to cosmic structure as the existence of black holes themselves. The anthropic principle suggests that our universe possesses the specific properties necessary for the emergence of observers precisely because only observable universes can be selected from the vast ensemble of possible cosmic architectures. In this view, conscious observation is not incidental, but essential to cosmic existence and meaning. If this interpretation proves correct, then your capacity to understand black holes is not accidental, but represents a necessary consequence of physical laws that must produce both gravitational extremes and cognitive sophistication. This would imply that consciousness and black holes are co-emergent aspects of any universe capable of sustaining organized complexity and producing observers capable of contemplating their own cosmic context. Regardless of philosophical interpretations about cosmic necessity, your scientific capacity to comprehend these cosmic extremes remains factual and extraordinary by any measure. We have developed theories that describe precisely objects impossible to visit, measure directly, or reproduce in terrestrial laboratories. Our mathematical equations predict the behavior of objects we will never touch, located at distances we will never travel, operating under conditions we will never directly experience. This conceptual transcendence demonstrates conclusively that physical limitations do not necessarily determine cognitive limitations for sufficiently intelligent beings. The fact that creatures confined to a single planet, with lifespans measured in decades and sensory ranges limited to narrow bands of electromagnetic radiation, can nonetheless understand objects containing billions of stellar masses, and spanning cosmic distances represents an almost miraculous cognitive achievement that may be unique in our cosmic neighborhood. We represent the possibility that the universe can understand itself through conscious subcomponents that develop sophisticated mathematical abstraction and conceptual frameworks. Every equation that describes black hole physics represents a victory of mind over the limitations of direct sensory experience. Every successful prediction about gravitational waves or event horizon dynamics demonstrates that abstract thought can transcend physical constraints to achieve genuine cosmic understanding. Each mathematical relationship discovered through pure thought, from Einstein's field equations to Hawking's radiation formulas, represents a triumph of conscious reasoning over the apparent impossibility of comprehending cosmic extremes. When Stephen Hawking showed that black holes must radiate energy, he was using nothing more than abstract mathematical reasoning to discover a fundamental property of objects he could never visit or measure directly. We are literally the universe that has awakened to contemplate its own most extreme structures through emergent cognitive processes. The atoms in your brain were forged in stellar cores dispersed through space by supernovae, gravitationally organized by the same forces that create black holes and somehow arranged into patterns capable of understanding their own cosmic origins and ultimate destiny. This cosmic self-observation through conscious minds might represent the most profound phenomenon possible in the known physical universe. A collection of matter has become aware of itself, developed the capacity to study its own behavior, and achieved understanding of cosmic processes that operated for billions of years before consciousness emerged. The universe, through you, contemplates its own nature and discovers its own mathematical beauty. Your physical insignificance makes your cognitive significance even more remarkable and precious within the context of cosmic immensity. The fact that something so small can comprehend something so vast suggests that meaning and significance operate according to completely different principles than mass and energy. Your capacity for understanding represents a form of cosmic importance that transcends every measure of physical scale. Contemplating the largest black holes teaches us appropriate humility about our physical scale, while simultaneously inspiring legitimate pride in our unique cognitive capabilities. We are reminded of our cosmic smallness while celebrating our intellectual achievements. This balance between humility and pride, between cosmic insignificance and cognitive triumph, defines the mature human response to cosmic immensity and beauty. We exist as conscious bridges between the world of everyday experience and extreme realities that completely transcend human scale. Through scientific understanding, mathematical modeling, and conceptual frameworks, we connect familiar concepts with cosmic phenomena, translating the incomprehensible into the merely difficult, making the impossible seem merely improbable. This function of cosmic translation makes every human being an active participant in the process through which the universe comes to understand its own fundamental nature. If you're still awake, it's because the content was really good. So take a moment, leave a like, and subscribe to the channel. It helps a lot. And if you want to keep watching, just click on the video that's appearing right now. I'll see you there.